All right, now that that's behind us, sorry, we're having a few technical issues. All right, so I only received one question, and that was regarding looking at the reaction of DMSO and the dehydration of alcohol. So, based on the question, there's a misinterpretation of what's going on here. So let's say I have this compound here. So this is what was used on the discussion board. So it's 2,2-dimethyl cyclohexanol. And I want to run two different types of reactions. One reaction, I want to look at H2SO4, and the other one I want to look at tert butoxide. So these are the things that are actually doing the chemistry, but what you'll sometimes see written underneath these is DMSO. Sorry, it's showing me on the back end that you're not actually seeing my video. So if you're curious why this suddenly appears, this is why. This is so weird. Come on. You can do it. So I'm going to keep going, and I'm going to check in the background to make sure that this is still like loading. But if I have to repeat myself, that's fine. Anyway, DMSO here is the solvent, dimethyl sulfoxide. So I'm going to go off the top of my head. This may be wrong, but I think this is. So it's probably something that looks like this. So DMSO is a polar aprotic solvent, and this kind of gives us the ability to work with ionic reagents. So it's something like diethyl ether. If you added H2SO4 to it, it would exist as a crystal of H2SO4. If you added this tert butoxide, it would exist as a crystal of tert butoxide. So DMSO is one of those compounds. It's polar enough to dissolve ionic compounds, and this is why it has such a high dielectric constant. This is why it looks like it would favor an SN1 mechanism, is because it has such a high dielectric constant. But that said, it does kind of sit in that intermediate ground where it does allow ions to form, it's just not very good at it. So something like water would be really good. So when we're running in DMSO, it's more saying that we're having to run it because whatever we're working with is a fairly ionic reagent. Now, something like H2SO4, what it's going to do is it's going to protonate the alcohol, which is going to pop off, and we're going to get the SN2 mechanism, or the SN1 mechanism. So this will result in carbocation rearrangement, and ultimately we will get the 1,2-cyclohexene. Now, if you work with something like tert butoxide here isn't going to promote a carbocation. It's not going to protonate the alcohol. Most likely what it's going to do is it's going to abstract some hydrogen from over here because of how big it is, and when it abstracts that hydrogen, that's how we're going to end up with this one here. So the 3,3-dimethylcyclohexene. So DMSO here is not a reagent, it's a solvent, and it's a solvent that we work with when we need to work with polar compounds, but because it is aprotic, it doesn't have free hydrogens, it's more likely to promote a, in this case, an I kept saying SN, E1, E2 mechanism. So, and if we're running substitution reactions, it's more likely to promote an SN2 reaction over an SN1 or an E2 over an E1. That said, it does, as people have brought up, especially Niall has brought up quite a bit in the live streams, it will do both. It is a high K dielectric solvent, high E dielectric solvent. So what it's likely to do is actually allow both of these to occur. So most likely you're going to get a mixture. But yeah, hopefully that addresses that question. I know that's a long answer, but the short answer is that DMSO is not a reagent, it's just a solvent. So it doesn't really participate in the reaction, but it does stabilize certain intermediates. Good, on my back end, it's kind of showing that this video is running. I'm going to be really annoyed if it's not. Also got an email, and I'm going to respond to this email asking about free radicals. Do they follow the same trends as carbocations? Actually, they do. They tertiary radicals are more stable than primary, which are more stable. I'm sorry, which are more stable than secondary, which are more stable than primary. So let's say we have this hypothetical molecule. If we put a radical here, it's going to be more stable than a radical here, which will be more stable than a radical here. Now, the thing we get with free radicals that we don't get with carbocations is rearrangement. So with these radicals, we don't have the ability to rearrange the molecule like we would with like a hydride shift. But really, I would say that's the big difference. The stabilities follow the same. I have a video up on YouTube about it. I personally do not understand why. With carbocations, there's kind of an explanation as to why one is more stable than the other. But with free radicals, I've never seen a good explanation for why a tertiary radical is more stable than a secondary, which is more stable than a primary. I'm going to go with this as YouTube server because everything else is running fast on this computer. All right, so if you got questions, put them up in the chat. Otherwise, I'm just going to kind of mess around until 3:30. What's up? Go lay down for your nap. Because you're tired. Aw, go lay down, sweetie. still curious how it looks with the handwork. What's up? You really want to be held, don't you? Oh, little girl. There you go. Poor little rich kitty. Every day is a new struggle. Stray cats on your front porch eating your uneaten food. Birds outside just out of claw reach. Somehow you soldier through. Do you need me to hold your tail too? Oh, looks like a question finally made it through. 40, 72, and 74 on the homework. All right, let's see if we can do this with a bad stream. So organic 2, questions 40, 70, and 72. I'm sorry, 40, 72, and 74. Oh, there was so much fur in that. So I will try to work these on the board behind me in case YouTube has decided to go to really low resolution. All right, so show the mechanism of how the starting aldehyde is converted to the enol form using the mechanistic arrow. So these are these are acid catalyzed conditions. So with our base acid catalyzed condition, the first thing we're going to do is protonate the oxygen. So the oxygen is going to take its lone pairs and attack the hydrogen to give us water. And if it's okay with y'all, I'm going to leave this as just a big R group. So the R group here is that benzene ring plus the bridging methyl. So this gives us an R. Oh, actually, I still need that methyl group. Sorry. Methylene group. So this can be our first compound, and I'll try to switch it to the desktop for you so you can see it. Hopefully you can see it when the stream's over with. So it starts you out with those lone pairs. They're just going to attack a hydrogen, and then we're going to break the bond between the hydrogen and the oxygen. And we're going to finish with water. And our final structure, so I'm going to get it drawn. Sorry, there's a lot of fur on me right now. Make sure you got the plus in there. All right, so the next step, all right, it worked. Next step is we need to get oxygen back to its desired valence. So we're going to break this oxygen carbon bond to give us basically a carbocation. That probably would have made a lot more sense if I showed you on the board, showed that to you on the board behind me. So next step, we're going to take this complex here. We're going to break the carbon-oxygen bond to give us the carbocation. So I'm going to draw it draw the mechanism, draw the structure. And the big trick with this one is probably remembering that you do form a carbocation, so make sure you throw the charges in there. All right, the last step, we've got water. And so what the water is going to do here is we've got a hydrogen. It's going to attack the hydrogen. This is going to kick down to give you the double bond. And you're going to finish up with your enol and hydronium H3O plus. It's actually looking like it's asking you to do a lot more than that, but we'll get there. There you go. Getting asked, do I see the chats? Yes, I do. Unfortunately, right now it's looking like a 10-15 minute gap. All right, question 72. All right, what's the structure form of the reaction of aniline with acid aniline and hydrogen as a nickel catalyst? Y'all keep asking me amine questions. I'm not that good with amines. So this is aniline. Acid aldehyde. Okay. So acid aldehyde here. First thing we're going to do is we're going to form the amide. So we're going to attack there. We're going to displace the OH group, and we're going to end up forming, as the first intermediate, this compound. Now, this can, trying to remember, if we put this over a catalyst, this will form the alcohol. So the H2 will cause this addition, and the subsequent addition will result in elimination. So now that's a lot. So let's take a step back. What's going to happen first with the aniline and the acid aniline is we're going to displace this OH group, and we're going to form, I think it's called an imide. Again, not so good within nitrogen complexes. When we hydrate it, or we hydrogenate it, we're going to start with this. But what's going to happen is that we can get elimination. So what will happen is that this oxygen will extract the hydrogen from the nitrogen, and through a series of rearrangements, we end up forming a nitrogen-carbon double bond. So I'm going to think, I think I'm right now, so let me switch to the desktop and let's see if I'm actually right. And I'll work it out here for you on the stream as well. So what'll happen first, so aniline is this compound here, NH2. And our acid analyte is, oops. Oh no, it's not acetic acid, it's acetaldehyde. So sorry. Back it up. Sorry, got acetic acid stuck in my head. This is your acetaldehyde. So with the acetaldehyde, you'll immediately get this substitution, so you don't need to worry about displacing the alcohol. But again, the hydrogenation here is still going to give you the same outcome. Actually, it won't. So you're going to get attack to give you this compound here. The nitrogen has a lone pair on it. This is going to react to displace the oxygen to give us an OH minus. And this OH minus is going to abstract a hydrogen to give us, make sure you can see it, this compound here. So hopefully it's a little bit easier to see in this program. So we start with the acetaldehyde. Which is this complex. The acetaldehyde is going to react with the ammonia, or the nitrogen on the aniline, to first give us oh, you're being so difficult. Okay. I know this is a lot. I'm trying to draw it for you so you can see it. So we'll end up with this intermediate. Now what's going to happen is two things. One, this oxygen is going to abstract a hydrogen to give us an OH. But then this nitrogen is going to further use one of its lone pairs to make a double bond and break off that OH group. And then that OH group is going to pull the hydrogen off of the nitrogen to give us this compound here. So this is just the reaction of the aniline with the acetaldehyde, is we end up producing this imide here. Subsequently, it says you're going to react it with a hydrogen nickel catalyst. So what that's going to do is break this double bond here, and it should give us, oh, come on. The N-ethyl, oh, stop it. The N-ethyl phenyl amine. So that's what I'm thinking is going to happen. So let's take a look. Yep. So again, it's kind of a long, drawn-out process here. But what happens is that that lone pair on the nitrogen attacks the acetaldehyde. We initially form an alcohol. That alcohol further dehydrates just naturally with nitrogen to give you the imide, which would be this complex down here. And then we're going to hydrogenate. All right, question 74. Oh, this one. All right, so question 74. I remember this one not because I actually know how to do it, because I did it yesterday. I got it wrong. Okay, so we start with this compound. And we add a hydroxide. So this trimethyl amine group here is actually a really good leaving group. So what's going to happen is this OH is going to abstract the hydrogen. This is going to kick down to form a double bond, which is going to break this bond. So what we're going to end up with, and again, I only know this because I answered it yesterday and got it wrong, is this compound here. So yeah, this is a named reaction. I forget what the name of it is, but I do remember this is an elimination reaction. So what you end up getting is the alkene. So if I bring it back to the desktop, that's my complex. Oh, you're being obnoxious. It's dinging me because I was lazy with the stereochemistry. There, are you happy now? Yes, it was just upset over the stereochemistry. All right, so that's 60, 72, and 74. And again, the only reason I knew the Hoffman elimination was the only reason I know it's called Hoffman elimination because it just told me it was a Hoffman elimination. But it's a Hoffman elimination. All right, so at this point in the live stream, I'm going to cut it off on my end. It's not that it's done, it's that there's so much buffering on your end that if you asked a question, it would probably have to take like an hour, hour and a half to get this video to compile. So on my end, I'm not answering questions. If you do have questions, feel free to email them. Um, but yeah, otherwise, thanks for coming. Uh, yeah.